Yeah. Uh, Hello, everybody. Welcome to the seminar. Today, it's my great pleasure to introduce Dr. Parisa Mirbod. Uh, she is currently an associate professor in the Mechanical and Industrial Engineering Department at the University of Illinois at Chicago. And she received her PhD degree from City University of New York and did a her postdoctoral training with Professor Jeffrey Morris at the Benjamin Levish Institute in New York. Dr. Mirbod has built her career on deriving innovative theoretical, computational, and experimental methods for fluid mechanics, particularly in complex fluids with particle-laden flows and through permeable surfaces. Her research has been funded by agencies such as NSF, and DoD, and she's received the I at UNITO Faculty Fellowship from the University of Turin, and has also received the NIH IFPA New Investigator Award from, I guess, NIH, and she's also a recipient of the NASA Glenn Faculty Fellowship. Her talk, which you can see the title of on the screen right now, is one I'm particularly looking forward to. So without further ado, I welcome Dr. Mirbod.
Thank you very much, George, for the nice introduction. And thank you also, Hussein. It was great meeting you all. Although I know some of you already and I've talked to you via Zoom for different research and some other collaboration that might happen. So today I want to talk about the particle migration over porous structures to flow transition and instability in non-colloidal suspensions. This work is specifically supported by Army Research Office and NSF. Here is the outline of the works that I'm going to cover. I'm not sure if we have enough time to cover all of them, but first and foremost, I want to start talking about flow analysis of suspensions over porous models in the experiment that we are performing in my lab using PIV and PTV, and also with collaborator using MRI. Then I'm going to talk about some instabilities in Taylor-Couette flow with particles, and later onset of Rayleigh-Benard instability of suspensions, that actually these are all related together. And in the meantime, I will show all of those scenarios. So here you could see some examples of free flow over porous structures that researchers actually extensively investigated the natural streams of flow over canopies, coral reef, and even the flow of preciliary of the lung airway. And also we have discussion, and where I was PhD specifically was working on red blood cells and the flow over endothelial glycocalyx, that you could see some samples here. Even the flow over granular beds and flow over superhydrophobic surfaces have been investigated by a lot of researchers. On the other hand, there were some works also that consider suspension flows in various geometries, like Couette flow or in channel or different structures. But specifically, the goal of my work, and when I started my career, I coupled these two scenarios. So meaning that the flow over porous media are now coupled with flow over with suspensions. And it is anticipated that this coupled flow of suspensions over porous structures or permeable surfaces, they have a lot of applications in both laminar and turbulent regime, that here you could see some of those applications. For example, microbial devices, manufacturing, processing, pharmaceutical and food processing industries, as well as oil, chemical companies, and even mudslide and the motion of mudslide over the surface of the earth, which would be example of porous structures. So to examine these, we proposed two scenarios. The first one was looking at an experiment of analysis of suspensions using PIV, PTV in my lab, and also MRI. As you know, there are some challenges with PIV, and when you add particles, specifically we have to index match the particles, and these are really important to decrease the reflection. For example, here we use PMMA particles, and the size range of them is around 95 micron, I would say plus and minus 20 micron on the size. The working fluid, we use the 73% glycerin plus 27% water, and the reason was to have density matched and index matched with the PMMA particle that you could see some sample of it here. But unfortunately, there are some challenges for PIV. For example, if you add more particles, more than 5%, the flow would be really faint and vague, and it's hard to see what's going on. What we have done as a first step, we use the channel. The channel is pretty long, it's around 2 meters long, and at the bottom of the channel, we use different structures that are 3D printed. Here is one of those porous structures that is made of rods. To add more particles and to go even with 40% suspension, that would be even interest in some of those oil companies or even in some of those other scenarios in biomicro devices. We then switched to MRI, and I collaborated with Professor Mina Shafi at Rutgers University. That first I'm gonna talk about that in detail. We used a mouse MRI that has an aspect imaging of around 1 Tesla was the magnet, and it was pretty small. So we used a 2-meter channel inside it, and as you could see in this image, there is a pump and there is a flow that would be in a loop, and we were trying to analyze the flow inside it. One of the beauty of MRI, also compared to PIV and PTV, was 3D structure of it. For example, we could get different slices and then gather and collect all of those slices to get a full 3D version of the flow. However, in PIV, we were able to do that with 2 cameras, but specifically, I'm going to talk about the 2D scenarios in this. So here, I'm going to start with some of the analysis that we did with the MRI. This slide shows the intensity images taken from MRI for 30% suspension. Then the flow rate is only 70 milliliter per minute. The flow meter for MRI must be very small because, and the Reynolds in this case is just 0.1 because of the application and limitation of the MRI. We couldn't go to higher. It's just, it should be very small so you could capture what's going on in that case. So what the way that MRI works, when you have the channel, before you add any suspension, you must first add the pure fluid inside it and do some calibration. Then we emptied it and add the particles. So these 3 slices are actually the slices, the top view. These dots are the structure of the bottom surface of the channel. And this is a slice that shows the flow in a free flow region. This is at the interface, and this slide is actually in the middle of the rods that you could see an example of it in here. What is most interesting here, and we could see, is the dark region and the light region. So the dark region are actually showing the collection of the particles. And you could see there is a wide band of these dark particles in the middle, followed by other dark bands that are near the walls, one in here and one in there, while there is white band in between that shows there is less particle in that. We could faintly also see in these images some darker particles that are appear in between, but of course we have to do some analysis. So we then did some analysis, and here are showing some of those axial velocity maps where we had analyzed the flow, and this shows the particle migration and the velocity of the particles. So as you can observe, for the pure fluid case, which is the concentration of 0, and also 10%, 20% concentration, we could see the maximum of velocity inside the free flow region and also in between the rods. Not that these are all for the slices on top of the rods, and these are all for the slices between the rods. However, when you add more particles, go to 30% and 40%, there is minimum velocity in between. However, there is maximum near the edges of the channel. This is in agreement with previous studies, specifically when the aspect ratio is very low. Here, our cross-sectional aspect ratio is just 3.75, and that's why we could see a maximum velocity near the edges of the channel. It should be noted that if this is wide enough, you shouldn't see any of those maximums. So definitely these maximum near the edges are due to the Wall effect. Then we analyzed using the phase encoding method with the scan sequence of spin echo diffusion weighted images. Here are some of those velocity profiles, and again show that we will have a maximum of velocity that are actually appear close to the interface. But when we add more particles, a plug flow or blunted flow appears, and the velocity profile would be much less. What we did next was to further analyze the concentration profiles. And here are 3 slices: axial, sagittal, and coronal slices or images of those concentration profiles that actually, if you look at the figures of B, E, D, and F, you could see there is a periodic suspension flow over at least 9 to 10 rods that definitely shows the flow is periodic, and it's kind of fully developed. If you look at the other view, which is called axial images, and it's actually YZ plane, you will see there is a maximum on at the middle or center of the channel, which is due to the shear-induced migration. However, we also observed that the concentration of particles would be also maximum in between the rods. So meaning that the structure would help a lot to change the geometry and migration of the particles. What was more interesting here that we found is that we have a banding of particles. There was one question here, and we were also interested to see if this is a banding actually happen, and that interestingly, we did the test for different scenarios. You can see here some of those for different concentration of the particles. Here is 10%, then 20%, 30%, and 40%. you actually see for 10 and 20%, the particles are all uniform. But when you add more particles, the structure of the porous surface made this occur, or the banding actually happens in this scenario. So is we then also analyze what's going to happen for top of the rods and in between the rods by analyzing again concentration profile. And here it shows a concentration profile that is occurring inside the system. Let me just where for 30% there is a uniform velocity profile on top of the rods, and in between the rods, however, by adding more particles, the particle migrate to the middle of the channel. It should be mentioned that when you have a smooth channel, it already the other researchers have shown that there would be, due to the shear induced migration, all the particles gather in the middle of the channel. But here, what is different from those is that we found there is a maximum in free flow region for higher concentration, and then this particle migration will decrease inside the rods, while for 10% we have uniform concentration of the in that case. So this means that by adding more particles, the maximum definitely occur inside the free flow region, and it would be much less inside their rods. Okay, so that was one of the results that we got, and mostly in the MRI, but then we wanted to try what's happening with the PIV. And in the PIV, here are some of those cases for 1%. All we could do with PIV was just 1%, 2 and 3%. Still, we are working with some other scenarios, and there are some papers in preparation. But these are some of those analyses that we got with the PIV, the concentration profile, again, the maximum of the concentration. And as you can see in the map, and also we averaged everything that we got from the between and on top of the rods. We averaged all of them, and here is the concentration profiles that show again the maximum, even for very few particles of 1, 2, and 3%. The maximum of concentration occurs inside the free flow region, while we have another maximum that is also occurring in between the rods. So again, the same scenario of particle migration and having the banding occurs when we have the less particles of, let's say, 1 to 3% in that scenario. We were also interested to consider different cases. So here, for example, delta is the depth ratio that shows the H, which is the length of the free flow or free gap, to the L, which is the thickness of the porous, and then sigma, we call it permeability parameter, and is the length of the porous divided by its permeability. We use some formulas that are already published to define the permeability for this case, but what we have done more was to changing the thickness of the rods, and also to change the porosity, which is epsilon and 0.9 in those scenarios, and also the permeability of the rods, and see what's going to happen in all of those cases. It should be noted that in all of those scenarios that you could see, those little red dots are actually seeding particles, and the the large particles of around 95 micron are actually index match. Maybe sometimes you could see some of them that are not really index match, or due to the temperature variation, something gonna happen here, or you could see some of those that are, for example, this one, you can sometimes see them, but there are definitely suspension flows and are different from the seeding flows in there. What was interesting, and we define, as you increase sigma, or in other words, change the permeability and decrease the permeability, the location of maximum velocity profile goes to the topper wall, while when we change delta, the location would be close to the interface. We also analyzed and examined the dimensionless slip velocity for different sigma and delta, which is depth ratio and permeability parameter. Then what was interesting here was the numerical methods, and we wanted to actually prove if there is any numerical method that we can use by coupling of the suspension with porous media. As you may know, there are some methods that are called mixture model for suspension. So meaning that when you have a suspension, and here is example of our channel, we have a suspension on top, porous media on bottom. We try to model and combine the so-called suspension balance model, which was proposed by Nathan Brady and Maurice and Boulay. And when I was postdoc, I was working on that. Then we were trying to couple those with the Brinkman equation, and also volume average Navier-Stokes, which is the so-called Vance equation, and to find out if we can actually find out a model for all of those analyses. Here are some of those numerical methods and DNS with the suspension balance model. And then we matched all of them with the results that we got from PIV, PTV, and MRI. So this is a velocity profile and another velocity profile. These are for concentration from 1 to 5%. That shows all of those results from the numerical method. And the pink circles are actually the experimental results from the PIV. As you can see, there is a pretty good match between the experiment and the free flow region. Inside the free flow, however, there is a mismatch inside the rods and porous media. For MRI results, the velocity profile is obviously so different, and we could see a huge velocity profile that is producing inside the porous region compared to the rods that we considered in our experiment. And also there is a mismatch between the concentration profile and the concentration profile of the model, a suspension balance model, and the experiments. And this is not surprising. And first of all, because in the experiment, we consider the particles are actually moving inside the rods. But in this model, the porous media is, there is no particle motion inside it. And this is one of the reasons that we did some analysis different. And recently we are using IBM, and I'm going to show you in detail some of those results as well. When with IBM, we got some interesting results. So here is one conclusion of the part one, that we use PIV, PTV results for dilute suspensions, and those reveals that particle migration both within the porous structures and in a free flow region that are totally different from smooth. And with MRI, we could even go with higher ranges of the suspension, ranging from 30%, 10% to 40%. That shows banding, and it would be interesting to see the banding. I have to also mention that we did some linear stability analysis using suspension balance model that was produced in the Army proposal, but nor base state, neither base state nor perturb solution could capture with suspension balance, and then that's why we had to move on to other scenarios. Here are the three published papers that are actually related to this part one. What was interesting, and we found, actually I had a postdoc that was working on Rayleigh-Benard suspensions and Taylor-Couette flow of pure fluid, and then we were discussing about, might be also interesting to consider if there is any analysis with the suspension. And it's surprising that we didn't find any numerical simulation that considered either Taylor-Couette flow or Rayleigh-Benard with suspension, while there are a lot of experiments and numerical simulation with pure fluid. So as you know, really, Taylor-Couette flow has a lot of application in drug delivery, bioreactors, blood vessels, graphene production, and all of those are some examples of Taylor-Couette flow. But when there are red blood cells or bubbles or particles in any scenario involved in the system. However, as I mentioned, mostly there were experiments by the time that we were working on this paper. So we proposed in this case to consider Taylor-Couette flow inside a Taylor-Couette system. As you know, for this specific paradigm or phenomena in fluid mechanics, is easier to consider the outer wall fixed while the inner cylinder is rotating. Specifically to compare our results with the experiment, we ran our cases for the exact scenario that happened in the experiment. So for example, we consider the radius ratio 0.877, the length ratio 4, and we considered also two different particle size ratio of 60 and 200. All of those analyses that I'm showing here are for the case of suspension 10%, but recently we have results for other 20, 30, and 40%. The different scenarios are happening, and these are either accepted with some revision or they are in review. I'm going to talk about that in a minute. What was another important parameter here that we considered? Because we have suspension, then the Reynolds of suspension would be involved, that the Reynolds of suspension actually considers the viscosity of suspensions as well. And we found that for this specific case, the suspension Reynolds number would be around 180 for some of those cases. But the particle Reynolds number is always small. So although we have rotation, the particle Reynolds number would be always very small in all of those scenarios that we are dealing with. That is a best fit for suspension balance model. We use finite volume method, and here are some of those information for numerical simulation. And here you could see some of those analyses. So what is interesting for any kind of instability problems that I'm sure George is very well aware of, that is to first analyze the base state and then apply the perturbation to the system. So before we move on to higher Reynolds number at Reynolds of around 110, and for a concentration of 10%, here are some of those results, which is actually the Taylor-Couette flow would be end up with a simple shear, and all of those results would end up with circular Couette flow or CCF. This graph shows the concentration profile, and this is the azimuthal velocity profile. So in between the cylinder. So meaning that if you add 10% of the particles in before any perturbation or before any instability due to the Taylor that happens, we just have simple shear flow, and there would be a minimum accumulation of the particles near inner cylinder, while we have more accumulation near the outer cylinder. And obviously the velocity profile would vary because the inner cylinder is also moving, but the other cylinder is fixed due to the slip velocity. The velocity would be small. We then increased the Reynolds number, and the goal was to then characterize the nature of the instability. And we used Landau model, using the model that was proposed by Landau and Lifshitz in 1976. And this is the formula. In this formula, sigma is called the linear growth rate of the perturbation, while L is the Landau constant, and the norm of A, or the amplitude of the perturbation, can be defined by analyzing the norm of the axial velocity using this formula. I'm not going through the details, so all of those details are already published in our JFM paper. But what we have done here, we actually try different Reynolds number, and for each Reynolds number we characterize this amplitude, and then we matched it with somehow Landau model to define sigma and later L. For all of those values, the extrapolation of drawing the sigma, which is linear growth rate of the perturbation, versus the Reynolds, finally showed us that the critical Reynolds number occurs at around 120 for both 60 and 200 particle sizes that we were dealing with. We also, in this paper, as you can see, we compare it with all of those experiments or linear stability analysis that we founded. So these three are the experiments of the same scenario, so meaning that they added the particles inside the wet flow, and with either PIV or LDV, as I remember, they analyzed the same with the same scenario that we considered, and they got very close to critical Reynolds number that we found 120. It should be mentioned that this critical Reynolds number is based on the viscosity of the suspension. If we consider the viscosity of the pure fluid instead, the critical Reynolds number ended up to be around 160 for a concentration of 10%, while for the same scenario, we know that for pure fluid, the critical Reynolds occurs at 120. So this means that adding particles is actually stabilizes the flow. We were also interested to use this model and to define the nature of the instability. It should be noted that in general, this parameter DLN of the normal amplitude to the dt versus the square of the norm of amplitude shows the nature of the flow. And most importantly, the slope of this line, it actually shows if the flow is supercritical or subcritical. So meaning that if L is positive, the flow would be supercritical or non-hysteretic bifurcation, while when L is small, we have subcritical bifurcation. And interestingly, we found that for this case, the flow is supercritical for both particle sizes that we consider. We then increase the Reynolds number. So remember, for this case, the critical Reynolds number is 120, but we increased it a little bit more, and is 100 at Reynolds of around 125. Here are some of those space-time diagrams that are usually shown in Taylor-Couette system. So here is showing the radial or azimuthal velocity profile. This shows the vorticity in the radial direction, and these are the axial vorticity, velocity, concentration, and shear rate. What is interesting in all of those scenarios, you could exactly see the Taylor vortex flow or those counter rotating rollers that are occurred in between the flow. But what would be then interesting, and we found in here, when you add particles, actually those rolls that are producing this make some shear, or the shear flow would be shear gradient is actually very low in the middle of the rollers. And due to the shear, again, induced migration, all the particles gather inside those rolls. And you could see that we have either in this image or in this image that all the particles are getting inside the rolls that you will see in those slides. We increase more the critical Reynolds number, and the Reynolds number to 135. Still, we keep 30% concentration, and the particle size is 200. You see that the wavy vortex flow occurs where there is oscillation that are appearing on the appearing for the rollers. And what was interesting here, still there are some particles that are gathering inside those rollers, but these are very non-uniform. So it seems something is happening which result in changing the shear-induced migration and the particles. And in general here, this slide shows the concentration and the distribution of particles for Reynolds of 135, 150, and 170. As we could see, by increasing the rotation of inner cylinder, or in other words, when we increase the Reynolds number, what is occurring is the particles are getting more mixed. And this, another scenario, the axial oscillation of the wavy vortex flow state will change, and then by adding by increasing the Reynolds number or rotation rate, there would be insufficient time for the particles to undergo the shear-induced diffusion, and then there would be all uniform dispersed particles, or in other scenario, this would help a lot to the mixing of the particles. So what was also interesting and is also important in all of those scenarios that we are dealing with when we have Taylor-Couette system is the transition scenario. Here we also observed and compared our results with the pure fluid flow when we have a Taylor-Couette with a Newtonian pure fluid. First, simple shear or circular Couette flow occurs, covering by Taylor wavy flow and Taylor vortex flow and wavy vortex flow. Then we also discussed about the critical Reynolds number that is around 120 occurs in here by adding the particles. And here again the concentration is only 10%, but we have different size ratio of the particles. We could see that is still the same scenario happens CCF, TVF, and WVF. However, by changing the size ratio, another scenario, which was a spiral vortex flow occurs in that case that we couldn't see for other scenarios. It will be also interesting, and I have to note that by adding more particles, and even we found there is another modulated wavy vortex flow, and also ribbon that are occurring inside the system. And these are all in the papers that are in review or would be published hopefully soon. So to conclude also part 2, particles dispersed in a viscous fluid led to the stabilizing the flow, and also we showed that the obtained critical values show a good agreement with all those previous experiments. Their primary instability appears to a supercritical or non-hysteretic bifurcation, and there were some other analysis, such as we also showed that the torque and friction coefficient and also the pseudo Nusselt number would be all impacted when you add the particles. So what was interesting here, we showed that the suspension balance model, although when we couple it with the porous media, couldn't capture what was happening in the experiments, but we definitely could apply suspension balance model if, although this model has some of those terms that are not considering analysis, and most importantly, it should be applied for Reynolds when it is low. Here we applied it for very high Reynolds number, and we got very good results. So I don't know, do I have time? Can I continue, or do you want me to have 1 or 2 slides and
maybe perhaps, yeah, you can finish in a couple of slides. Yeah.
Okay. So if this is the case, then I ignore the last part, which is actually linear instability, and we worked on the onset of thermal convection in non-colloidal suspension in a Rayleigh-Benard problem. Here are some of those. I just ignore showing all of that, and perhaps jump to the conclusion that when we have 2 plates, which is a phenomenon of Rayleigh-Benard convection, then one of them is cold and the other is hot. As you know, a convection occurs in between, and there would be a flow that there is a flow between these 2 plates. We found that the critical Reynolds number actually increases a lot when you add particles in the system. And also we showed that the transition arises through a subcritical bifurcation, which is totally different from the case for the pure fluid inside in that. And also when we have suspensions inside the Taylor quet, there were some other analysis and also a new published paper that we worked on the Rayleigh-Benard with particles. So last and foremost, I have to say that all of those analyses that I showed so far was actually for flow of suspensions when we use a mixture model for the particles and combine it with the porous media. There is another work which is, we are working on that currently with collaboration with Luca Brandt in Sweden, and his postdoc that is now in Japan, Marco Rosti. What we considered and we published is that instead of just a mixture of particles, here we used IBM or immersed boundary method, while we have the collision of the particles and the lubrication of them, and also collision between the particles and the valve involved in all of those analyses. In this specific case, we have a channel, which is on top and bottom, we have porous media, and we coupled the immersed boundary method with the porous media. And interestingly, we found that even the particles are not moving inside, either for very low Reynolds number or for a very high Reynolds number, which is kind of turbulent flowing suspension. We still could see banding that is occurring inside the flow. So meaning that the porous media actually does some interesting analysis and changes all of those. So with that, I would like to conclude my work here. And here are my PhD and postdoc, some of them actually that are working in my lab or either graduated, and my collaborators, Harunori Shikawa, Luca, and Nina, and some of those works, and also the support from NSF and a new NSF grant that hopefully we continue on analyzing more on the suspensions over porous media. With that, I would like to thank you, your attention, and I'm happy to answer any question you might have.
Thank you very much for interesting talk. I think Dr. Choueiri is still there. Please go ahead and post your questions in the Q&A or in the chat room. Let me see. Dr. Choueiri, are you still there?
Yes, yes.
Okay.
Waiting for student-related questions. I know some students who are eager to ask some questions about this. But if while we're waiting, I just want to thank you, Dr. Mirbod, for a great presentation. Sure. For those who've done work with this complex fluid, let's say, we know how difficult and challenging it is, and how great the progress you're making is in the field. So thank you for sharing some of that with us.
Thank you. It's a pleasure. Thanks.
Maybe I can start off with the question in the first part that you had this flow over pillar type structures.
Sure.
You know, I do a little bit of work with materials, and we have basically been working on these nanowires, CNTs, and other materials that basically they're mainly used for electronic application, but we were using it for printing application. So we were basically using them to soak in a colloid and then use that for printing purpose. So what is the status of work in terms of analyzing the fluid over posts that are basically not rigid? They're like bendable, like hair or brush, if you imagine.
But so are you talking about the suspensions?
Yeah.
In this, I'm not aware of any specific works on this region. I would say it would add perhaps more complexity, and I'm happy to talk to you if you are interested into that. That was one thing that we were working on that. We were planning to work on that in future. I know that there are a lot of work, and as I showed you, for pure fluid, and even recently viscoelastic or non-Newtonian fluid, but these are all without any particles involved. When the particles are added to the system, some of those scenarios that I would say, as also George mentioned, having the particles inside the system would be a challenge, because usually in PIV or PTV, you will need some seeding particles to track them and get the pure fluid. But when we have the particles, those particles must be either index matched, or there should be some other ways to see what's going to happen when you have large particles. That's from the experimental part. And even if you have, the deformable rods or any other structures, of course, it would be another complexity to that. But that is also interesting. And in the modeling case, I'm also aware of some of those analyses of the pure fluid over brush structures, that those brushes are also moving and deformable, right? That again, these are all pure fluid, but when you have the particles, that would be different scenario. So I'm interested work on that, because I think what was I proposed first for both this grant and NSF and Army was we're gonna get something from rigid rods or pillars, and then we move on to the deformable and flexible, but it didn't happen yet. So
Right.
it was all challenging that we were dealing with the rigid surface, but for sure it would be really interesting to consider deformable. Yes.
Sounds good. Yeah, I might reach out in future about that because we had one case that we couldn't understand the interaction of these colloids with the deformable kind of brushes,
Right.
and they were micron scale.
Other question that I can, if you are talking about the colloidal particles, then it would be nano ranges, right, of the particles?
Micro to nano ranges.
Yes, so that would be even another complexity to the system, because in those cases, Brownian and colloidal suspensions and Brownian equation come into account that would be even more complex, but it should be interesting to look at those as well. Yes.
Thanks for the comment. Thank you. Dr. Choueiri, I am not seeing here. Let me see if the Q&A here.
Yeah, I don't see in the chat questions, but I can ask some questions as well. Regarding the Taylor Coet simulations,
Yes,
were these
sure.
were these particles simulated as well, or do you just simulate the concentration for the migration and whatnot?
Are
Are you
you
actually?
you
Yeah.
mean the interaction of the particles?
Yes.
No. It's really complicated. We
Yes.
tried to use it. We tried, and we talked about that even with Luca, because Luca had, he has a lot of codes with immerse
Yeah.
boundary method and different analysis, and it's really expensive to consider it in Quet flow. And perhaps one of the reasons that we found it novel and we published it in JFM was nobody has used a mixture model that we used it. I didn't go actually through the equations. I refer you to please look at the JSM, but in general, in this model, what we have, we actually have the particles inside the system. So meaning that we have a Couette flow, and instead of the pure fluid, we have a non-Newtonian fluid. But in all of those analysis for suspension balance model, the particles are involved. So meaning that there is a formula for viscosity of the suspension, that this viscosity depends on the concentration of the particles, and also the stress and pressure stress that are due to the particles are also coming in one term in all of those models. Actually, suspension balance model was proposed by Nathan Brady and then Maurice and Boulay, and they worked on this analysis, suspension balance model, and it was defined from the experiment of MRI. So we use that for this Taylor Couette flow. So meaning that it's just kind of non-Newtonian, but very perfect non-Newtonian model that can be easily applied to case of Rayleigh-Benard or Taylor Couette flow.
All right.
But it's very complicated to
Well, I was kind
consider.
of
Yep.
yeah, I was quite impressed by the simulations, thinking that no, there's no way that the particles could be simulated here as well, but just a concentration.
Yes, exactly.
Because what I was thinking about, which was kind of, yeah, sometimes some things aren't practical, but you have some thought experiments you're just curious about. So I was wondering what would happen in the case where you had all the particles collected near the center.
Mhm.
What would happen if at that moment you start changing the density of the particles? How would they start to behave very slightly? And the application to this could be some kind of chemical reaction or something like that that could be happening. And I was just wondering if it's possible that the particles will migrate away from the center and create, very different scenarios just by a imperceptible change of their densities. But I guess these things take. Can that be done with the current models?
But with the experiment, I have to say, as I showed you, there are very recent experiments, but these are all experiments that they have done. I can maybe quickly share those papers. Let me find that. Excuse me. Let me find that and share it with you. Let's see if I can also share. See my screen. Okay, could you see my screen here in this page?
Yes.
Yes. So these are Maji et al. Actually, is Maji. It was in Jeff Morris lab. Sorry, and they have done some visualization method. These two papers, they actually use PIV. They added different particle concentration and they analyzed the flow characterization and all of those, as you mentioned in their paper. And these are pretty new. I'm aware that these guys, Ramesh and Alam, I actually I believe I reviewed another paper from them, and they are working more on getting PIV. So that's on the experimental side. But for computation, our computation was the first, and we are still working on that. Of course, there were some differences between whatever they found in visualization and PIV with the numerical method, but we found it very, very similar. And it shows that this model, although is a mixture model, it would capture everything that is coming from the experiment variable. Actually, we have a paper in review now that would be out soon, and we exactly got all of those regimes that they are seeing for PIV and visualization.
Yeah, it's quite exciting.
And if you want to see more, I think in their paper, Ramesh, because they use PIV and density matched, they also mentioned about that, density matched problems and the variation of the temperature. And they mentioned how by adding some little surfactant to the flow, they try to make it density match. So make sure that the particles are all the same. There is no sedimentation and all of those.
Well, that's quite challenging. So we're trying to figure all that
For
out.
PIV is interesting. And I think they are working on that. Yeah. So I definitely refer you to those papers. For now, we just focus on DNS. We found it very well. So we are continuing on that part still.
All right, great. Thanks for sharing your recent results.
For sure. Yeah.
Any other questions or comments? Sorry, I have to go to another meeting at 2 o'clock. I'd like to thank you again. Very interesting talk. Looking forward to learn more and hopefully work with you in future.
Yes, thank you so much for the invitation. I'm sorry that I couldn't make it because it was last week a conference here. And then apparently, I don't know if Society of Rheology was here. And
was it? Okay.
First time in Chicago, and I attended. And then after that, I figured out a lot of people, they got COVID, and I was also sick. So then, these are all happened that I couldn't make it to come over. But
still great that we can have you virtually, and hopefully we can host you in future.
It was a
Thank
pleasure.
you again.
Thank you, George.
Thanks, George, for organizing this.
Yeah, thanks. Hussein. If you want to leave, Hussein, that's fine. I think I'm a moderator here. I can just close up.
Okay. All right. Thanks.
Right, thank you. All right. If there's no other questions, I'd just like to, again, on my behalf, thank Dr. Mirbod And somebody here is asking, is it
Go ahead.
possible to account for different types of particles?
In the modeling, no, I would say no, is not, at least for this specific no cases. I'm not aware of any situation because all of those models are based on a monodispersed particle size. So this means these are all the same. But there are some recent work that are dealing with polydispersed and different type of particles. Actually, this is an interesting question. They are recently working on different size of the particles, deformable particles. For example, in bioreactors, you have red blood cells, and in other bio devices, you have red blood cells. So these are all deformable particles. But for now, I'm not aware of that, or we cannot do that currently.
All right. Well, it's kind of exciting times because things have been developing very quickly, but whether we'll in our lifetime get to a point where we can simulate at the Reynolds numbers of interest, I guess, with the concentrations of interest and all the properties, time will tell, I guess. But
Sure.
any other questions before we, I guess, end? Okay, so I'd like to thank you all. Thanks again, Dr. Mirbod, and
Thank you.
hope to keep
Thanks.
in touch and
Sure.
see more of your work in the future.
Thank you. Yes, looking forward talking to you, hopefully in future, and seeing you.
Yeah. All right.
Thank you. Thanks. Thank you, everyone. Bye. Have a good one.